Notebooks out. Laptops away. That's because you're waiting on your laptop.
Is this still Jake?
Yep. Do you think from last day, move on that quickly?
Oh no. Yeah.
Last day we left off here. Conjugate acid-base pairs. The new terminology is conjugate, and it's a acid-base pair that differs only by a proton. So I showed, as I think the bell went, we have an acid, acetic acid. Water here is acting as a base because it's acting as a proton acceptor. Becomes the base and the acid. We can also write this in the reverse. H3O plus. And that way we have the acetate ion acting as a base. In which case we have an acid and a base making a base goes to make acid and a base. And we get the same conjugate acid-base pairs. Which is obviously leading into the theme of the entire year, that this can be a reversible reaction. It can go either way. The pairs we're looking at is anything is an acid on one side. When it is on the other side after it's reacted, it has become a base because it's lost its proton. If it's lost its proton, that means on the reverse reaction, it's going to gain a proton again, and that base is going to accept that proton and then become an acid. So these are known as acid-base pairs, and they differ by a proton. And then I'm going to have you write out a whole bunch of them. So late. Okay. Good. What I'd like you to do, finish off these reactions, identify the acid and the base, start off on your own, and then I'll probably have you go up to the board with someone else and also work them out, and identify the acid-base pair explicitly. In much the same way I did here, where I labeled them A and B for acid and base.
Can you go down on that page? Or did you not finish it up?
Pardon?
Can you go down on that page that you just said?
Did you come in late? 5,
Is that different?
4, differ. Rhymes with tiffer. Although, if I text recognize, it's diffoo. So finish off those reactions, identify the acid-base pair. Ooh. Oh no, that'll work. You'll need a hint for the last one. We'll wait for you to get closer to it. And now I will quickly take attendance. Okay, I'll ask you to grab your partner, head to the board, start writing out the equations. Someone will know how to do it, and then you'll be able to look at them, see how they do it. I just did it on the previous page, so stare at the one on the previous page. Try to fix that one. Grab your people.
That's what I thought made sense. And then this is,
Is that correct?
Not completely correct. It looks like you're looking at someone else's. What's a Bronsted-Lowry acid and base?
hydrogen is one
What's the
proton.
difference between it and the original acid and base?
Came from the second one.
Does that make sense?
Negative.
That is the cleverest way to get a wrong answer I've seen. No, because like that is amazingly clever. You've done the right thing. You just have to do it the other way.
Oh, okay, so it's just a story actually.
Oh, take one.
Don't forget your charges.
NH4 plus OH.
There you go.
And then you're gonna get the acid and base.
Oh, Max, you did what I just told the other group.
New film. Let's do the next
You did that wrong in the cleverest way possible. Other way around. You'll never get NH2. And don't forget your charges, by the way. Protons are moving around. They have a charge.
Other way around.
What do you mean by move as far?
Well, you moved the hydrogen around
Yeah.
correctly. You forgot the charges in the products, but other than that,
Oh, so it was correct.
no, because the correct part was that you moved the hydrogen. You just moved it the wrong way. Which one of those is a base?
That's what makes the base.
H2O is whatever you want it to be.
Yeah, I think we
It's twice the chance of a David on Saturday night.
I don't want it to be an acid. There we go.
Well,
Mr.
NH3, what's that?
I forgot.
Pardon?
I forgot.
It's a base.
Oh.
It's ammonia. So that is definitely a base. So bases are proton. Oh, I'm not telling you now. You have to look around.
Say,
I told you from the first
so,
one.
so we make a hydroxide.
I didn't know this makes sense.
We are making a hydroxide.
I know 3. I thought it was like
down
2.
You know what you're gonna
I don't know.
You're right.
I don't
No
know.
way.
No way. I was just going off of what you said. I had the same thing you guys said.
Yeah, you did. And you've corrected it. You've also forgotten all your charges. Other than that.
Yeah, but I'm trying to get through all of them now.
Oh, no, do the charges right the first time. You'll create a bad habit if you always drop your charges. Get your charges on the first
how does it
one.
become NH4 though? I still don't understand.
Look at theirs. Where did he get the hydrogen from? From the acid, which is water.
Yeah.
So the protonolaric acid bases are proton donors and proton acceptors. So you have to move the proton around.
So that things that
You just take one away, put it on the other one.
Okay.
Yep. Is that, what's the charge in a hydrogen? There you go.
There we go.
Yeah, that's one.
H and
That's also NH. Oh yeah, base and acid.
But that doesn't change, right?
Is that the acid?
That's what you're supposed to do.
This one?
Yeah.
Is it H?
Yeah, this
The
one
goal
is
is
secondary.
under- The goal is to make it an acid base. So
This is negative.
That's it.
let's make it
And
a
then you just switch.
No,
Wait, so it has H to the back.
I think this one has
This is negative H.
Wait, bro.
Well, it's
It ends at OH. What is CH3CO? What is that? Is that CH3CO?
This one. Which one's gonna take too long?
I know this is a base. This is a base. Going forward is the rest. If you take away the H. Look, it's only do you have a notebook?
yeah, okay.
Now, who's got number 2?
CH3COO
Choose theirs because like
plus SO4
What's the last one?
Also, Max, check your charges.
Minus one because they got a plus one.
Second one especially. There we go.
Okay, I'll read out the next one.
Gleb, check your charges on the second one.
HCO3 minus
and a
plus
minus the SO4.
S minus 2.
Alan, check your charges on the second one. Charges look good on the second one.
Is it actually small minus?
Acid H. So that's it.
Yeah.
No, it's because it says H. It's an acid. That's negative. So it has to be base.
Theo?
That's great.
Oh, I'm good. As people do it, I'm going to go around and take a look, and then if everybody's done it, I'm going to.
Okay, so
It's got your system.
So we got an acid, base, base, acid. Pairs
Oh, you're
so it'll be
So this one.
CH3COH.
Is there? Yeah, there's one. Yeah. So
You got the
it has to be
CH3COH one? Oh, nice.
It's always
accepts pH as a base.
Yeah, which is a.
Now you just switch it around.
There you go.
Because now
Well,
this one could take.
If it was going that way, it's
Donate an H to this.
definition of a base.
So it's always like acid base.
This one,
always.
donate this H.
Okay, HC.
Oh, for the fifth one,
This one can donate this.
I need to give you a hint.
So it's acid base.
One of these is really close to a strong acid. Which one of these is related to a strong acid? SO4. H2SO4 is a really strong acid. Strong acids can never be on the product side. So if your version has a strong acid on the product side, it just won't happen. You have to make it the other way around. Also, as you're going through, identify the acids and bases. Some of you have and some of you hasn't. Put little A's and B's if needed. And either join them or write on the side the pairs so we can see them.
So both of
Which one is
Everybody, yeah, everybody seemed to get that one. Let's switch up colors.
If it starts like H, actually has this is just like oh, it's like H3 is like weird. If it starts with H, it's acid. Right.
Wait, but why does one of the? Because that's what
This one.
That's a D, yeah.
How are we supposed to know, bro? Like all this.
No, but look at it.
yeah.
You just made an H and S.
You get this one. Yeah. And here, same thing. This one can donate. And here, this one can theoretically donate two H's.
I think I understood.
You get this. So if you look at this, like you said, this one's close to strong acid. So this one's gonna go in here. Yeah.
Okay, wait, there's one more.
I don't know.
There's nothing on acid. Oh, there is no.
CO3 minus.
There you are.
I don't want to get into this.
You know what the scales are? What are the numbers that acid and base chart goes?
HSO4 minus 3
Hey, Mr. McCall.
Yep.
Why is CH3COO minus and HSO4
And what?
Why are there two minuses on the product side?
This one?
Yeah.
If you take a proton off of this one, what charge does it have?
A positive.
Well, what charge is a proton?
A proton's a neutral.
A proton is not neutral. What's the charge of a proton in an atom? Positive. And it's a proton transfer theory, so we're always moving a proton without an electron. So if you take that positive thing off of there, what you're left with is negative. When you add the positive thing here, that has to be one less negative. So you're always moving a positive particle around. So your charges will always change, which is why when I'm going around and checking, like, change your charges, double check your charges. Green would still work. Hmm?
Could you hold for a second? I just want to see.
Check that one? Yeah. To be explicit about it, I put the pairs on this side as well to show, no, don't update my computer, good God. On the side so we can see the acid-base pair. These are all the acids, and these are all the bases. That's not reflecting on what side they're on. And in each case, we have group. And let's lock. There we go. Perfect. Excellent. I'm going to do that. Let's make it faded. There we go. And smaller. And lock. There we go. So Brunson Lowry is an acid-base system in which it's all about proton transfer. A proton from last day is a hydrogen without an electron. It's got a positive charge. So you have to decide which one's the acid. For the first one, water is neutral normally. So it's not an acid or a base unless it's forced to be one. It will do either one depending on what its partner is. So water is very popular, twice the chance of a date on Saturday night. It can be an acid, it can be a base, it can be whatever its partner wants it to be. So ammonia, household cleaner, it is definitely basic, it's a proton acceptor. It never donates protons. So what we're doing each time is that the hydrogen is here, water is going to act as an acid to this base. This is our proton acceptor, it moves over here. Test, enter here, and then do that. Because I can hear you all the way up here. When it's moving from here to here, the other part that's moving is the charge. So if the hydrogen moves from water to NH3, then this goes up by that hydrogen, but you also have to change the charge. That charge has moved from here over to there. Another way to very quickly check is when you're going through, the charges on each side should still add up. So the total charge on this side is 0. The total charge on this side is 0. The total charge on this side is -1. The total charge on this side is -1. So although that charge moves, the total charge never changes because all you're doing is moving that proton. So this becomes +1, that becomes -1, which is 0. Over here, the acid is clearly NO2, HNO2, because F- can't be an acid, it doesn't have a proton. So that proton is hiding right here. It transfers to there, and you get HF. That goes up by 1 charge, so that's 0. This goes down by a charge, so that's -1. Here, now this is an organic acid, and I heard some chatter. How do we know that's an acid? Where did that come from? Just a reminder, if we went back, it's one of these types of acids. And they're often written like this. And CH3 is the most common one you're going to see. So whenever you see this, that hydrogen can pop off. That's an acid. And despite it having an O there, it's not a base. That comes off, just like that. They can have any sort of R group there. And you can have more than one. The other way that you can see that is sometimes if you're an inorganic chemist, you'll see it written like that. Those two are the same. They're just irritated that we're writing the hydrogen at the end, so they wrote it at the front to let you know that's the hydrogen that comes off. It is not written biochemically accurate because the hydrogen's in the wrong spot, but it's written in a way that pleases the inorganic chemists because they like their hydrogens on the front because they're lazy and they're not used to thinking. Right, so a strong acid, that's in the next section. A strong acid is an acid that reacts 100%. So strong acids don't have equilibrium. They go to completion. And so if you ever have a strong acid on the product side, that can't happen because it would immediately react the other way. Yes?
I have a quick question on the last equation.
Okay, I'll go through, finish them?
Yeah.
Because I think I did all of those. I don't know if I finished this one. So here we have our hydrogen that's important. That one is just locked inside. It transfers base because it's a proton acceptor. And that way you have it. And the charge goes down by 1. Now we have -1, whereas before we just had -2. We have HCO3, bicarbonate. That has to be the acid because the other one can't give away anything. So that hydrogen transferred. This will go down to -1. This will go up to -2. Now for the last one, you cannot have a strong acid. And that was the hint I gave you sort of partway through. Many of you probably already did it. If you wrote this, at this point, oops, this looks completely appropriate given everything I've told you. I haven't told you about strong acids and strong bases yet. And so if you could be forgiven for saying, well, why can't we do this? Because this looks very amphiprotic. It looks like it could accept, they both look like it could accept or donate. We know, what type of acid is that?
Strong.
It's a strong acid, and what's it called? You're familiar with that. It's the one used in car batteries. Oil of vitriol. In the 1980s, Britain had a spat of people going around with this and shooting it in people's faces. It was a terrible, terrible time. This is sulfuric acid. It's a strong acid. And strong acids, as we'll learn in the next section, if you're a strong acid, you only go in one direction. There's no equilibrium. So strong acids only go in one direction. There's no equilibrium, it would just go that way. So if it just won't react to get there because as soon as it does, it would go there. So you have to find a different reaction that would work.
Does the H2SO4 need a negative charge as well?
This one? Oh, this one would need to be -2 for that reaction. Thank you. Yeah. But this is not a correct reaction because you can't make a strong acid on a product side. It won't go there. So for here, you have to look which one of these is not the strong acid Mr. Neufeld told me about. Well, H2SO3 is a weak acid. We can pair up that way, and this reaction actually will happen. So the only way this reaction can happen is that the HSO4 loses another one, and that becomes HSO3 and becomes H2SO3. So that goes down to another negative charge to -2. That goes up to 0. Now, if you take out your data tables, as I said, this is the very next section. But we don't expect you to memorize all the strong acids. That would be horribly cruel. Turn to page 6. I might as well put it up on the board. And then tell me what you see at the very top. Look at the shading, what it says. What does that mean?
The ones at the top are stronger.
Yeah. What numbers are they giving on the very right? Yeah.
Really tiny numbers. Small numbers.
They're not all very tiny numbers. Agree to disagree. Let's scroll down, page 6. These are all tiny numbers, but what number's at the very top?
Very large.
Very large. If you were to write a KQ for this,
Very large.
you have products over reactants. These are so large that essentially they go to completion. Notice they're also one-way arrows. So these are all your strong acids, and they're the only ones. Perchloric, hydroiodic, hydrobromic, hydrochloric, nitric, and sulfuric. So H2SO4, HNO3, HCl, HBr, HI, HCl4. Do you have to memorize all the acids? No, you have a table that tells you every single acid you know, tells you the name, and then it tells you the formula. Doesn't tell you the name of the base, you still have to figure that out. So hydrofluoric makes fluoride. hydrogen sulfate, HSO4 in equilibrium, that can go over and makes sulfate. So these are all of your acids that we would expect you to be able to know and look up. And you can also tell that we've done KQ, we've done KSP. What is obviously coming next? Ka for acids. And there will also be Kb for bases. You don't get a table of KBs because you can figure them out from the Kas. Because if you know the acid, then you can figure out its conjugate base, and from that you can actually figure out its Kb. So that'll be in the future. So strong acids have one-way arrows, and that's why this reaction isn't correct. Now at this point, we haven't done that. That's the next PLO, that's K. But we might as well start introducing it now. Does anybody have any more questions? Oh, I didn't finish off this last one. HSO4 is our acid with SO4 minus 2 as the conjugate base. The acid for the other one is H2SO3, and its conjugate base is HSO3 minus. Questions about any of those? Why did you write it a particular way? Where did the charge go?
For the, like, where does the SO4 and SO3, like, how do you know which one to use for the H?
For this one, for this one, if it was any other species, you wouldn't. And later on, what you would do is you'd figure out which one's the stronger acid. But for this particular case, I know it cannot make H2SO4. Because H2SO4 is a strong acid, you cannot make it because it goes the other way. It only can be a reactant. Because it will go, so as soon as you make it, it would just force the reaction back and it wouldn't happen. So if you make a strong acid, so if you have, say, if I gave you NaCl, plus HI, and I've seen this written on grade 10 exams written by other people. Double replacement reaction. This is actually an acid base in terms of chemistry 12 because we have a proton acceptor there because the Na is going to be a spectator in all this. What would our products be? Let's not make it I. Actually, the reaction will work better if I make that F. There we go. Pardon? HCl plus F minus. On a grade 10, I'd go, yeah, that you, sure. But this, if you look at our table, this is a weak acid. It has a Ka that's really small, so it doesn't react that much. This is what type of acid? Strong acid. So this doesn't have a two-way arrow. It has a one-way arrow, and it goes that way.
Wait, why is it strong?
Pardon?
Why is it strong?
Why is what?
Why is it strong?
Oh, just because it is. And to, like, because right now that's the point I'm trying to make. But if we go back to why is it strong, we would, if I asked you on a test, like, why is that strong? We would go back to what makes a strong acid? Its partner needs to be electronegative. So we've got chloride, it's electronegative. But we also had fluoride, which is very electronegative. It's not a strong acid, HF. The other thing it needs to be is kind of large, so that they have a long distance relationship. It's easier to let go if they have a long distance relationship. And so HCl, the distance is just long enough, and it's just electronegative enough that when hydrogen wants to leave, it wants to leave really fast, and they don't want to see each other ever again. Yeah.
So in like a reaction, is it just the weaker acid is the base?
Yes. The way you phrase that is confusing in that if it's possible to accept, like if it's both possible to accept a proton and it has a proton, it could go either way, then the weaker one would be the base. Because for a lot of them, there wasn't a choice. That's HNO2 and that's F minus.
No,
That
like
has to be the
NH3
acid.
and like H2O.
Yeah. If you have pure H2O, Is it neutral, acidic, or basic?
Basic.
Pure H2O? Like just a glass of water? It should be neutral. It's not a strong anything. It's just neutral. Whereas that's ammonia, which is a strong weak base. Clean solution. It's on our list of acids and bases and properties you should know that we did earlier. Does that make sense? Yeah. Now you'll start getting used to writing in the table and using the table. That will actually can tell you a lot of that. But I'll save that for when we actually start using the table a little bit more. Filling out some of the bottom. As you saw, some of them can be both. Those are known as amphiprotic. Oops, and apparently I can't spell. Amphiprotic can act as both a proton donor and acceptor. In order to be amphiprotic, you need to have a hydrogen. But you also need to accept a hydrogen, so they're often negatively charged. Often have a lot of lone pairs of electrons, so they often fit this format, HX minus. The most, no, do some examples. So, look for things that are like HCO3 minus. That can go or HCO3 minus can move back and forth because it can both donate a proton and it can accept a proton. Take out your table of ions, not table of ions, the acid-base table I just showed you, and find some other ones. Okay, page 6. There you go. What is what? Oh, yeah, it should. Because these would go both ways. Oops. Don't do that with a highlighter. So.
Can there be two H's, like H2PO4?
If there's two H's and it's not negative, is it going to attract? What's the chemical you said?
PO4, so it is.
What? No, what's the chemical?
The hydrogen phosphate.
Yeah, there's like two different ones of those. Which one are you referring to?
H2PO4.
Yeah. That's a good example. What charge is it?
Negative.
Yeah. So don't drop your charges.
So as long as there's like an H and a negative, it can accept it.
Usually.
What's like an example of one?
I just did one. That's my next question after we fill a couple more.
HC2O4.
HC2O4 negative. Yeah, that works. Because that can go to H2C2O4 or it can become C2O4 minus. So it can either accept or donate a proton. Yeah. Yeah. Any other ones? HSO3 works perfectly. Now there's one example, I've just asked, what is the one that can't? Can you find one on there that cannot go backwards? HI. HI is not negative. I wouldn't guess that one to be amphiprotic. OH minus. Oh, OH minus definitely can't. I didn't think of that as an example, but you are absolutely correct because, oops, there we go. OH minus is pure base. It is on the other side of a one-way arrow. It will never go that way. So you have the oxide ion. It is only a proton acceptor, and it will make that immediately. There's one more. Actually, there's two more. HSO4. So if we look at the top, HSO4 cannot go that way. It's on the other side of a one-way arrow. So it's opposite to a strong acid. It cannot go that way. It cannot ever act as a proton acceptor.
So it can only go like both ways if it's like in the middle?
It can only go both ways. Yeah, if you see those double arrows, it means it can go like this. But if it's the product, like you can find HSO4 right here, acting as an acid. Where did I lost it right there? Don't add a bookmark. It's acting as an acid. It can go this way. It can go back forth. But it's also here. It's on the base side. It can never become the acid. It can never make its conjugate acid in that particular form. And that's because its conjugate acid is a strong acid. It has a one-way arrow. Okay. At the very back, I think it was Taz's group. One of the reasons they made, they guessed ammonia was an acid, which was a reasonable guess at this point, and made NH2 minus. NH2 minus can never be made. It says NH3 is on the opposite side of a one-way arrow, so you can never go backwards, and it can never act as an acid and give that up. It can only be a base. We'll be using the table more, but right now you can start using it to look up acids, look up acid names and formulas. You can see which ones are strong. You can see which way are they going to react. If I don't see them on the opposite side of a one-way arrow, then you know, oh, well, they can, if it looks right, they can probably act as amphiprotic. Okay? Okay, so we got our examples. What else do I have down here? Oh, just as definitions, give me a monoprotic acid. Monoprotic. Yes, give me an example. HCl works fine. Give me a diprotic acid. H2SO4. Give me a triprotic acid. H3PO4. And that's just to ensure that you are familiar with those terms. They will be used. They're not anything special other than mono, di, and tri, meaning what they normally do.
For the triprotic?
Pardon?
Would H plus work for the triprotic?
H plus?
Yeah.
No.
It's H3O.
Nope. That's a really good question. H3O plus?
Would it work?
No. All protons. I combined my S and my T. Must be available.
So would CH3COOH work?
That would be a monoprotic acid. Yeah. All the protons must be available to react. So HCl can react, that hydrogen can go. H2SO4 can react to become HSO4. HSO4 can react to become SO4, minus 2 and minus 1 respectively. H3PO4 can become H2PO4 minus 1, HPO4 minus 2, and then finally PO4 minus 3. But if you have H3O plus, that can make H2O. H2O can make OH minus, so you got diprotic, but can OH minus go to O minus 2? No. This is, and the other part is this is pure base. Every base, even if it's Bronsted Lowry, it's a proton acceptor, in water makes that. And OH minus can never give up that last one. So they have to be available. To your end, Andrew, CH3 CH3COOH can go to CH3COO minus, right? Plus H plus. So it's at least monoprotic, but these hydrogens are locked inside. They're part of the organic structure. They're not free to react. You're never going to take one off and make that -2. That doesn't happen. Okay? So they have to be free to react. Other examples or questions?
So the same would be for HCOOH. That'd be mono.
HCOOH.
That would also be monoprotic.
Yeah, that would also be monoprotic. Is that on your table somewhere?
Yeah, it's on.
Oh, yeah. That's, sorry. Yeah, that's formic acid, otherwise known as ant bite. So the only H on here that's available is that H. It's monoprotic.
Just even though there's two H's, it's just.
No, so if we don't know or don't get given the names of the bases, so do we need to memorize that? Like, is that?
You know them.
But like, what if it's like,
You know them.
like brand?
No, you know them. Don't worry about silly things. What one don't you know?
FeH2OOH2.
Fe. Oh, okay, give me the number beside it so I can find it fast.
It's like the first long one on the bases.
Oh, here?
Yeah.
Hexoaqua iron. Yeah, you would know that.
Yeah.
I'm not going to ask you for that. You found the one I won't. But like for most of them, that's nitrous acid. But you can just look that in your table of polyatomic ions. It's nitrite. So you have it. Yeah. Am I going to ask you those ones? No. Later on, we do it in class and we name it and I show you what it is. But you, in practical speaking, you just look them up and you use the equation. Any other ones? Okay. Did I leave off any writing there? Nope. What is, okay. Conjugate acid. So from the last one, what is the conjugate acid? How do you identify an acid? What does it have? It donates a proton. Has the proton.
I was looking for in the same place.
Well, how do you know which one's the base? Accepts the proton. So it lacks the proton. Okay.
You know what she's in it. He's in the coffee too.
Taz, question?
No.
Are the pages messed up?
Yeah.
Okay.
It's okay.
They might be duplicated. I noticed afterwards there was a partial page that was duplicated. Apologies for that. The last one is, if you've already been writing acid-base reactions, we did a couple that reacted with water. The last two learning outcomes, or know and be able to do, is every acid or base can react with water. So for a base, the general form is base plus water goes to its more positive form plus hydroxide. Acid, HX plus water go to its more negative conjugate plus H3O plus. Every acid and base does this in water. And so even if they're not reacting with anything else, they do these. So let's write some reactions. Maybe I shouldn't be so mean right away. grab your partner, do those 4 reactions on the board.
Can you go back?
Yeah, Susan, grab your partner, go to the board. Go out. Erase the old ones. Everybody got the partners? There you go. We'll do 3 acid ones after you do these 4 base ones. But just follow along with the first one as a guide. Change the charges as necessary. If you were very clever, you wouldn't have erased the first one. Because it was the exact same as the first one on there. Yeah, I wanted to see you erase it first. Well, it's extra practice. That means you get a little better.
Also, it accepts well, like the charge.
Oh, which mark?
Do we add it all?
Are they all just plus H?
Wait, but Mr. Newfield,
Yeah.
aren't these all
yeah, yeah.
bases?
Yeah.
Wait, do we
Figure
always
out what
add
that is.
water?
Are we gonna add two waters? Add 2 bases?
No, you're plus water. In every case.
Oh, is it water?
Wait, we can't do it.
Water can be an acid, water can be a base.
That would be the.
This, the very first one is also the very first reaction on the previous page.
Ones
Yep,
that are.
the first one for sure, second one, third one, fourth one. Pardon? There are no strong acids. That's a weak acid. H2SO4 is a strong acid. Also, I just wanted to make sure.
That does, yeah.
And then now we do
Both of these are oh, it's minus.
That would be the acid.
Check your charges. What's your total charge on the right?
How'd you guys have H2SO?
That's just because
In this case,
And how'd you get
H2SO
H2SO?
is to give, right?
Yeah.
So it has to accept an
wait, so we add water to these.
On the
add
left,
one
what's
H.
your total charge?
So you add one H.
Okay,
So
that's
one
nice.
Right, what's your total charge on the right? Right, so something has gone.
Also, the charging from the right and the left have to be equal.
You do need to change the charge, but you change it too much. Both sides should be the same.
One minus,
Well, it doesn't matter what it is, you know the left
I
side.
got it for you.
Well, you add one positive, what's 2 minus plus 1? There you go. This is minus 1, yeah. You just did 2 minus.
Oh,
Yeah, what's the total charge for this? Yeah, you fixed it.
That's so cool.
You were just adding one and moving the.
It's like math.
All of it is like OH minus.
Yeah, and then for acid, it's gonna be H3O
Bro, I think it's whenever it reacts with water, it's always gonna be OH.
You just have to remember like all the negative charges. Everything on top.
There? Higher?
Take a photo of the.
What? Don't, no. They're all around you.
No, well, you have to color it.
I'll wait. If you take a photo, you know you're never going to look at it again.
Well, I was gonna put it on.
That means they're going too fast. Did you do the one before? Okay. Then why did you
You can scroll down.
No, I want to look at it.
It's like a new version.
I'm just dumb, son of a.
I feel like I'm in Tron Legacy or some shit.
Now I stated this one, that these are all bases, and I asked you to react them as if they're bases. So even if they had the ability to be an acid, where this would donate it, make it your plus, you didn't because we stated these are bases. For amphiprotic ones, I showed you the table. There was a Ka associated with it. You can calculate a Kb, and then it turns out you just compare which one's bigger, and that's the one that it would naturally do. But if it's stated, you just do that one. Okay. Now let's do some acids. Yep.
If you go back up to like HPO4, isn't that more acidic than water? So wouldn't that be the acid?
I just said, I stated this is for examples of bases, so I just want you to practice writing it as bases. So, can it react as a base? Yes. You'd have to compare the Ka and the Kb. I suspect for your example right there, the Kb would be larger, and it would normally react as a base, because H3PO4 is an acid. H2PO4 is sort of middle of the road, and then by the time you get to the HPO4, that negative charge is so big it wants to start acting as a base again. So I suspect that would in fact be basic, but I don't know for sure until I compare the numbers. Your acids. Oh, let's do acids in red. H2O2, H3PO4, HC6, H5O7 minus 2. Only 3. Here are your new people. Erase the old ones, go write the new ones.
It's the same group.
Is it the same group?
No, it's not. I don't know. They're not. They're the same person. I don't want to grow up.
Dude, can you go back to the reaction?
Yeah, well, they're also, oh no, they're not on your page. Everybody got the partner? Yeah.
And whatever that is plus.
So it's gonna be
We gotta figure out what is that. This loses the H. I think it loses just 3.
Yeah, it's just gonna be, it's just gonna be H2O plus
how do they get OH minus?
Yeah, that makes sense.
So then there's 2 oxygens.
Yeah, so here's this 4 H's here.
There's 2 oxygens.
Wait, that's it.
Wait, are you sure?
Yeah.
It's actually H2.
Oh yeah.
Yeah, this is just, this here is just H plus.
HO2.
Jobs on this.
H2O.
H3.
Might work. No reaction. Literally just C6.
Might work.
No reaction.
No reaction.
H5. Oh yeah.
But then wouldn't that become H2 or something? There's like
Yep.
The third one ever be C6H607 instead of putting the H.
Oh, C6H607.
Like instead of putting the H.
One of the reasons we put the H in front is to let you know that's the acidic H. Those are just part of the structure. Pardon?
But it's 2 H's though.
It can be, especially if it's a COOH. Could be, and then you'll see it there. But that, if they did that, they'd probably write it like C6 H. No, they'd write that C5 H5 C double bond C double O. This and that are kind of the same compound. The problem is with that -2, it's actually C3.
1 H.
And H5. And for this particular example, because it's -2,
HC6, H5.
At least that's mine. I don't know.
H5. Okay.
and that gets really complicated to write, so they do that. So if this was not -2, it's just 0, you would just have a 3 beside that.
Wait, if you lose a proton, is that
Just balance.
If you lose a proton, you become more negative, yes. Because protons are positive. Very positive people. HO2 minus.
Loses that H. Yeah. So it's
H2PO4 minus. H2PO4. Don't forget your charges at the end. Don't forget your charges. Second one.
Okay, how does this one
Second one.
get
there's no charge on?
What?
On the second one?
Yeah.
But you don't have to charge on that.
Did you move a hydrogen? Then the charges changed. There you go. Overall, they stay the same, but the charge itself moves. Well, that's the we got charges, 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 charges.
HVOs are positive.
use it?
Basically,
That one needs to be big. Yes.
no, this has to be the net of this. See the net of this one is this. -3 left, one, -2 plus 0. They just have to be equal, they don't have to be 0. Yeah, no, it doesn't. H2O is always positive. Neutral H2O. And you add an H plus. And then they make H.
That's it for PLOJ. The rest of the class is yours to study. You have to, you got a test coming up. I am not on duty this afternoon, but I will be around. Give me a text or an email if you'd like to drop by in the afternoon and get some extra help.
Where's Tyler?
I will be away possibly all weekend. I'll
Where
be
are you
back
going?
Sunday night. Nowhere. I'm leaving for very good educational reasons. No. That's in 2 weeks. That's a week from tomorrow. Ms. Walensky is going to the anime convention.
So who's gonna be on duty?
Ms. Walensky, this weekend, all weekend. Me, next weekend, all weekend.
Oh.
Yeah. Any questions on the last page? I'll leave it up a little bit longer in case you want to double check them, but everybody looks like they got their charges correct. And you're now moving your charges around. Protons are positive, so the charge has changed, but when you add them up, They should stay the same. -2, -2. Neutral, 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 neutral. 9.2. A reminder, bring your headings on our test day. I want them on the day. If you're not quite done them and you're like, I just want to keep them, no. Because doing your studying after you write the test is pointless. It doesn't affect your mark, but it does give us an indication of what you need to do in order to improve on the next test. If you're doing old exams, I encourage you to do them in your Hebden book, because then I can see them and see how you're working, and if I see anything that I notice that would help improve, then that's helpful. You obviously don't have to.
New,
Yeah.
we have a test on J coming up soon, our quiz.
We'll wait this test before I start telling you about upcoming quizzes.
So it won't be like the week after,
Or the day after.
so it can be.
But I wouldn't tell you that now. That would stress you. Yes, always, Friday. Lunch. Bring your lunch down.
Wait, when's that help today?
This afternoon, 2 o'clock on that. Okay. Solubility has two things. It has stoichiometry and it has the KQ. So you know the KQ is just that, and your suspicion is right. It is just the amount of square. So it's not that. Because that concentration of X, if it in this particular case is the concentration of OH minus, then it's not double. But X in that case, when you put the 2X, it's not that concentration, it's the solubility. So if you have Mg, OH2, and you drop some in the water, and some of it dissolves and makes an equilibrium. That's the reaction. The solubility is how much of this whole compound dissolves. How much magnesium is in it? It is just X amount. So the concentration of Mg plus 2 equal to X. The concentration of OH minus, how much OH minus is it? 2X. Well, the amount is 2X. So the concentration of OH is 2X. There's no 2 in front of that. It's just that compared to the solubility, it's 2X. Yes. Then it goes 2x squared. That's its concentration. Now, if I had a different question that wasn't asking it in terms of solubility, I just said, yeah, if solubility is involved, if it's dissolving in any way, and in any way it's coming from the compound being dissolved in solution, then the amount of OH minus is going to be double that of magnesium. But if I had a question where I said, look up the KSP, so you have that from the table, and you have a solution, the concentration of OH minus is equal to 1.0 times 10 to the minus 3. What is the concentration of Mg plus 2?
Oh, we can even do 26.
Let's say, I don't know what the case is. Let's say it's 5 times 10 to the minus 16.
I just started wrote a blank.
Ooh, no. MgOH.
Should we do 26? Yeah, let's ask him about 26.
Oh, it's close. 5.6 times 10 to squared.
They were precipitated.
That's only for us.
And that's because we're asking for this. They've told you the concentration of hydroxide,
Okay, yeah.
right? Like they just told it to you. So there's no 2x there. You don't double it or anything because that's just the concentration. It's just that here the concentration also.
We're trying to like separate the negative, the anion.
Solubility, this
Yeah.
is for
Yeah.
if they're asking constant.
Yeah.
So something
And the
has to be
reason
soluble.
these are confused, like I was explaining
The
this
salt has to
to
be soluble.
Eric in the other class, and I think about a third of the class
Salt.
eventually.
Salt.
You do so
Yeah.
many questions that have solubility in them, your brain starts to go, oh, it has to be doubled every time. And then when you go back to easier
But the
questions,
salt
because we
has
did
to be
this in
soluble.
KQ,
Like it,
you never
why
made
must
it.
the salt be soluble?
But now we've done solubility so often that you had so many soluble equations, you feel this urge like I have to double it. Don't really know why. And that's because you've done all of those questions, your brain's just being trained, so you have to sort of train when to,
We
only
did
when
good
there's.
on that.
Does that help?
Yeah.
We did good on that. Without like.
Were you just talking about like the 2x,
Mm-hmm,
and you're only supposed to double it in solubility?
mm-hmm.
Well, when it's asking concentration, that's.
You want me to do one up there? Cause it's probably more than one person here.
No, I think I know.
Okay.
I don't know.
Like this is
Here, and then
this is
here.
like G.
So if I have some,
Here.
semi-equated, HCl, and H plus, HCl minus, right?
Yep.
And
We're getting ready.
One way arrow to the right.
say, assume it's too big.
Okay,
So,
well, it
so
says,
some other.
I'll pretend it's HF in my head.
Okay.
Yeah.
If it's asking for solubility, does that just mean concentration of HCl?
That's like the
Oh, God. This is an acid-base equation. Okay, if that was a solubility equation, so it was like NaCl, then the solubility is the concentration of NaCl in solution. Yes.
Okay, and KSB is concentration of Na times concentration of
Cl. Yes.
Also, do we do clarification?
Yeah. And acids and bases. Yep. And there's a couple questions like those in solubility, but.
You don't understand number 26. Yeah.
When adding a salt to precipitate chemical ratio, why must the salt be soluble? What would happen if it wasn't soluble?
It was just not mixed.
Right. So that's the same as asking, like, you want to set up your friend with a blind date. And the person you set them up with is married. Why is that a problem? Because they're married. If it's not soluble, it's not going to separate.
Why must it be soluble? Because they're already salt. If that makes it feel like salt.
Well, they're all salts. I think you're using the word salt to mean solid and not able to be separated. So if they're insoluble, they're not ready for the next attachment. They're not going to come apart in solution. They're not going to be available.
They won't be available to react.
They won't be able to react.
So they must be soluble in order to react. Yes, they're less soluble.
I thought so too.
No, no.
Wait, I need to write that down.
How do you know
I'm gonna forget.
the reason?
EG. Things that was not from the precipitate. So it has to be some can be any of these.
Yeah.
What did you just say?
What's the question? They won't be able to react.
Oh, yeah.
Yeah, come Tuesday.
The solubility to the 25 molecular in two ways of increasing the solubility.
Oh, shit. I'm
And two
doing
ways of decreasing solubility. So that's two sections in their notes. Which two sections? There's a magic phrase for one of them. But you're increasing and decreasing concentrations.
Yeah, but like, how do you know by adding something soluble that it increases the solubility?
That's the compound, right? So you have this. This is just a Le Chatelier's principle problem. What do you want to do first? Increase the solubility or decrease the solubility? Okay. So how could we make this go that way?
By adding more SR. Oh, wait.
But it's a solid. Do solids affect the equilibrium?
No.
No. So that won't do anything.
Temperature can
Temperature, we don't know if it's endo or exothermic. Yes, you could warm it up. So that would technically, if this is endothermic, which they often are, warming it up will dissolve more. But it didn't tell you the thermicity, so you don't know that for sure.
It's at 25 degrees Celsius.
They didn't tell you which side the energy term is what I mean. So there is two other ways.
Maybe like
Pressure.
Are they gases?
No.
No.
Temperature.
surface
No.
area.
Well, you tried to do it.
Concentration.
You tried to do it by increasing that side, right?
Yeah, if you increase surface area, maybe.
Still, it's the same concentration. The surface area doesn't affect
Or
equilibrium.
you just eliminate
So instead of increasing that side, what, you could so what could you add that would decrease strontium?
something that is force and precipitate.
Yeah. What would form a precipitate with strontium?
Yeah, I don't have.
SO4 2 minus.
So yeah. So you could add SO4. Now you can't add that SO4 2 minus. You have to add a salt that it is soluble with. So there you go. Na2, SO4 2 minus. That would work. So you could add that. What else could you add? You could precipitate that. You could also precipitate that. What could you add that would precipitate hydroxide?
Hydroxide, you could precipitate pretty much anything. So like, maybe calcium,
If it's calcium,
Oh,
you can't do Na.
yeah.
So we would want.
Oh no.
Shut up. It has to be low solubility.
What's negative and soluble with everything?
You shoot KMG.
Oh, NO3.
NO3. So you could use Ca,
NO3.
NO3, 2.
Yeah, because it's like a negative, not soluble in everything, but you need it to be not soluble with the low and so CA isn't soluble.
So both of these will precipitate one of those out, and when they go down, equilibrium will shift to the right, which will dissolve more, increasing the solubility. Now, on a similar note, how can we make it go the other way? How can we decrease its solubility?
Add more SO. We need to like
Make it more soluble. Oh my.
Yeah, so what could we add to make it go that way? We could add more SR. What kind of SR could we add? SR, NO3. It's plus 2, so we add 2 of those. What else could we add?
You can add something hydroxide.
With hydroxide, what kind of hydroxide?
You can add
NaOH. Perfect. This, just so you know, the magic word for this is the common ion effect.
Bye, kitty.
Thank you.